Okay, so welcome back. So we are starting today's afternoon sessions. Let me recall you that the first lecture will be in this room, and then the next two lectures will be split between this room and the Euler-Lagrange seminar room. I think it was used last week, right? So whoever knows helps other people to go there. But apparently it's in the terrace floor. Am I right? Okay, good. I've never been there. So it is a big pleasure to have Karina MARIN speaking to us. Karina MARIN is from the Federal University of Minas Gerais, and she will be speaking about Lyapunov spectrum of volume-preserving partially hyperbolic maps.
Okay, thank you. It's okay. Okay, thank you. I would like to start thanking the organizers for the invitation. As Julie mentioned, I'm going to talk about Lyapunov spectrum of volume-preserving partial hyperbolic maps. This is a joint work with Davio Bata and Mauricio Poletti. So let me start telling you which is the setting. I'm always considering a compact manifold. F is going to be a D-field. And I'm going to ask for it to be at least C2. And μ is going to be an ergodic measure. And as you know, by Oseledet's theorem, there are well-defined Lyapunov exponents. And an Oseledet splitting that is going to give information about the asymptotic behavior of the orbits. And this is almost every point. And in this talk, I'm interested in the simplicity of the Lyapunov spectrum. So I'm going to say that the Lyapunov spectrum is simple if every Lyapunov exponent has multiplicity 1. That is the same as saying that the quantity of the splitting here coincides with the dimension of the manifold. So just has simple Lyapunov spectrum. If the dimension of the bundles is equal to 1. Okay? And I want to understand the simplicity of the Lyapunov spectrum for diffuse. The main goal is going to be finding open and dense sets of diffuse that have simple Lyapunov spectrum. So that's the main goal of the talk. And for that, the first step is going to be to find a sufficient criterion for simplicity. So the simplicity problem has been studied in different contexts, mainly for linear cocycles. I'm going to give a summary of the results. And the strategy is always the same. You have a sufficient criterion, and you apply that criterion to prove the simplicity. So for linear cocycles, we have some results. We have the classical ones of Givard-Rougy and Goldstein-Marguli that are for random product of matrices. We have Bonatti-Viana and Avila-Viana for linear cocycles over sheaves. And we have some partial results by Poletti-Viana for linear cocycles over partial hyperbolic skew product. So these first two settings are the uniform hyperbolic setting. This is a partial hyperbolic setting, and the first thing that I'm going to do now is to state a sufficient criterion for linear cocycles over non-uniform hyperbolic maps. And I want to mention here the difference between these two, because this is the one that I'm going to use. These are results about simplicity of the Lyapunov spectrum for linear cocycles This one is in the compact setting. The sheaf has finite symbols. This is in the non-compact setting, and here the sheaf has countably many symbols, okay? So the classical approach of the criterion is to analyze two properties for linear cocycles that are called pinching and twisting. So I'm going to define now these two notions in the setting that we are interested. So first step is to establish a sufficient criterion for non-uniform hyperbolic maps in the base. So the criterion is going to be general, it's going to be for linear cocycles, but then I'm going to apply it to the derivative cocycle because I'm interested, as I mentioned, in finding open and dense subsets of diffeos with simple Lyapunov spectrum. So again, I'm consider a diffeo sufficiently regular. And I'm going to suppose that P is a G hyperbolic periodic point. This is just a notation that is saying that this is a lower bound for the rate of contraction and expansion of the hyperbolic periodic point. And I'm going to consider a linear cocycle. Which is alpha Helder continuous. And I'm going to say that it is C fiber bunched. If this happens, I have this relation for every point. So alpha here is the exponent in the Helder continuity, and this is saying that, the lack of conformality in the fibers is dominated by the expansion and contraction that I'm seeing in the periodic point, okay? And there is classical that in this setting, they're going to exist holonomies for every point in the stable or unstable manifold of the point P. So if I have the stable manifold of P, I have the fiber here, and I have a well-defined holonomy that is taking this fiber in this fiber, and this is true for the unstable also and for every point in the stable and unstable manifold of P, okay? So, which is a definition of these pinching and twisting conditions? I'm going to say that P, G hyperbolic periodic point, is pinching if, when I look the action in the fibers, this is going to be the period of the point. So this is a map going from the fiber in P to the fiber in P, and I'm asking for it to have all eigenvalues simple with different absolute value. So again, the goal is to have simplicity of the whole Lyapunov spectrum. I'm asking first for this condition only in one periodic point. And the second one let me. So I'm going to do the drawing first. I have dance table of P. I have this table. And I'm supposing that this point C is homoclinic, it's in the homoclinic class of P, so there is some iterate here in the stable manifold. And I know that here in the fiber, the drawing is not very good. I know here in the fiber I have simplicity of the Lyapunov spectrum. This was the hypothesis. Have unstable here, stable here, and have this point, and it's iterate here. And since I have that hypothesis about fiber bunches, I mentioned to you that we have holonomies, so there is an unstable holonomy that is going to take this fiber in the point C. I'm going to apply the dynamics to this iterate, and I'm going to have now an stable holonomy that is taking this fiber to this. So here I have unstable. Here I apply the dynamics. Here I have stable. And this is a map that I'm going to call phi. That is again a map between the fiber and P. It starts in the fiber and P and return to the fiber and P. And I'm going to ask for the eigenspaces associated to these eigenvalues to come back in general position. So if I have two subspaces that are sum of the eigenspaces associated to the eigenvalues, when I apply the map phi, it returns in a different position here. I don't know if you see colors, if I use colors here. But this is the fiber. I have the original ones, and the other ones return in another position. So I have this kind of result when A and F are eigenspaces which sum gives you the complete dimension. Okay? Yes? Yes, I need 1 point and one homoclinic.
Sorry.
Yes.
Thank you. You have this condition only for 1 point or for every point, or if you have for 1 point, it follows for every point?
The criterion is just for 1 point. I'm saying that the periodic point is going to be pinching if this happens.
For some point.
The point P is pinching if this happens.
Okay.
Okay? And the homoclinic point Z is twisting for P if this happens. Okay? And the criterion is going to be that only 1 point of this is going to give you. Okay. This is okay or larger than this? Okay. So, which is the result? F, again, is a diffuse. I'm going to ask for the measure μ to be ergodic. See, hyperbolic, this means that all the Lyapunov exponents are non-zero, and this is a bound for the absolute value of all of them. going to ask for it to be saddle type. This means that there is at least one positive and at least one negative Lyapunov exponent. And I have this condition I'm going to explain when it's used. It needs to be an equilibrium state of a Holder potential, or it needs to be an SRB. Any of them is okay. I have a linear cocycle with this C/2 fiber branches. And there exists P pinching and C homoclinically related con P twisting. And I know that this point pinching is homoclinically related to the measure μ. I'm going to define this. Then I have simplicity of the Lyapunov spectrum. Okay, so it's analogous to the classical criterion of simplicity. I'm using the pinching and the twisting condition. And now I have a non-uniform hyperbolic map in the base. The conditions are the existence of a pinching point homoclinically related to the measure and a homoclinic point of P which has this twisting property. And this condition in this point is sufficient to have simplicity of the Lyapunov spectrum. Okay? Any dimension. Okay, yes, I didn't mention it, but here is a linear cocycle, and there is no condition in the dimension of the linear cocycle, so it's general.
The pinching means all the eigenvalues are simple? Is that?
Yes.
Okay, yeah, thanks.
Sorry, this is really small, right? Okay, the pinching is that that is a linear map from RD to RD has simple Lyapunov spectrum, okay? And the idea is that this condition that is implicit in one point, jointly with a twisting condition, is going to give you simplicity in the whole cocycle. Okay, so I have this condition of the relation between the point and the measure. This means the following. So my measure is a hyperbolic. So I have pacing manifolds, stable and unstable pacing manifolds for almost every point. And I'm going to say that the point is homoclinically related to the measure if I have this condition. I have transfer intersection between the pacing points, the pacing manifolds for almost every point, with the stable and unstable manifolds of the periodic point. Okay? So let me make some comments about this result. I mentioned in the beginning that there was a sufficient criterion for linear cocycles over countable shift that was due to Avila-Viana. This is the criterion that we are going to use here. The proof of this result is a combination of the symbolic coding of the non-uniform map in the base to the criterion of Avila-Viana for countable shifts, okay? And so, going to remark the proof. I'm going to explain, I'm going to mention some, I'm going to make some comments in relation to this, but it's essentially a combination of these two results. I'm using here the version of Busikro-Visier-Sarik of the coding of the non-uniform hyperbolic map. And this is the criterion of simplicity of Avila-Viana in the non-compact setting, okay? So at the beginning, I mentioned that the goal was to have open and dense subsets of simplicity, okay? This has already been proved for linear cocycles. Over non-uniform hyperbolic maps. By Baques, Poletti, Barandas, Lima, Baques, Lima, Poletti, Baranda. The difference is that in that result, they have a sufficient criterion, but since they are interested in studying linear cocycles, they only have one coding. They have the fixed base, and they are going to study linear cocycles over that fixed base. So the criterion in that paper is a criterion in the cocycle, in the leaf of the cocycle, if you want, to the coding, okay? And that's a problem when you want to study diffuse, when you want an open and dense subset of diffuse. This was not working for us because we need a criterion that does not depend on the coding, because when you change the diffuse, you change the coding also. And that's the difference between these results and that result, okay? And this notion of homoclinic relation with the measure would allow us to present the pinching and the twisting in the original setting before using the coding, okay? So let me make some comments about the proof. I'm going to state the Avila-Viana criterion. So the Avila-Viana is for topological Markov sheaf, measure ergodic with continuous local product extractor. Linear cocycle with holonomies. And the same translated notion of pinching and twisting for 2 points that are in the support of the measure. Okay, so this is the criterion of Avila-Viana. And so, let me, here. We know that we have this coding that again is the existence of this coding for non-uniform hyperbolic map is a series of results of several people. I'm just using BCS because it's the one version that I need here because I have irreducible Markov topological shapes, okay? And I have the measure key here and the measure here. So I know that this exists, and I want to apply the criterion for this base, okay? So I need to check that I have this hypothesis, and the ergodicity follows from the result. The local product structure of the measure is going to be a consequence of this result. This has been proven in this setting for the measure being in equilibrium state of SRB. So the leaf of the measure is going to be ergodic and it's going to have continuous local product structure. The fact that the point is homoclinically related with the measure is going to give me 2 points in the Markov shift that project in the 2 points that I have, that satisfies the pinching and the twisting condition. And I need for those points to be in the support of the measure. And then again, this condition is going to give me that this measure has full support, so I don't need to worry about the points being or not being in the full support, in the support of the measure, okay? And again, it's the classical result that the linear cocycle being fiber bunching is going to imply the existence of the holonomy, so the twisting is well defined. So now I want to apply this criterion to state the existence of open and dense subset of partial hyperbolic maps that has simple Lyapunov spectrum that I mentioned was the main goal of this talk. So observe that, I will erase the thing, but if you recall, we have 2 conditions, the pinching and the twisting, right? I have the simplicity of the spectrum in P, and I have this general position when I consider the map phi. And it's, again, rather classical to have this configuration, because as Lorenzo mentioned, you always have periodic points, you always have homoclinic points. You can perturb your diffuse to get simplicity of the spectrum of P, and then since this is a homoclinic point, you have a very well control of the orbit of these things. You can make a perturbation here that is going to change one of the holonomies, so now when you apply, it's going to get in another different position, okay? So obtain this kind of configuration is rather classical. I think that it's clear also that this is an open condition, because if you have simplicity of P, you are going to have simplicity for the perturbed one, and the holonomies vary continuously with the maps. So this configuration is going to be open. The problem is that I need this also. Okay, so the idea would be to prove that there exists an open and dense subset of diffuse that satisfies the criterion. Okay, so satisfies the criterion is pinching and twisting, that we saw that it's okay, but now I need the stability of this homoclinic relation also. Okay. So the title of the talk is volume preserving. I'm going to focus in the volume preserving, but let me mention one other application. Yes.
When you change the dynamics, you also are changing the measure, and then you need some kind of stability of the...
Sure.
Okay, thank you.
That's why I focus on volume. Everything is volume preserving, and the measure is the same. But I want to mention one other application that is for measure of maximal entropy. Okay. So okay. I'm not going to be very precise here in the hypothesis because I want to state the volume preserving setting, but here, if we consider the setting of the works of Monjes Pacifico and Monjes Pacifico Poletti, These are open subsets of partial hyperbolic maps. This one, when center dimension is 1, has 2-dimensional center. If you were here in the talk of Juan Carlos, you know about this. And in the setting, we can prove that there exists U, CR open and dense, such that for every G in this set, the Lyapunov spectrum of any ergodic measure of maximal entropy is simple. Okay? I said it's a partial hyperbolic. Both of them are partial hyperbolic. This one is center dimension 1. This is center dimension 2. There are some hypotheses about the entropy, the topological entropy being bigger than the unstable topological entropy that was defined by Jérôme Bussy. And there are some pinchy conditions because you need that your co-cycle be fiber banded. I'm going to consider the derivative, so I'm going to ask for some condition in the derivative restricted to the unstable and stable to be dominated, okay? And in this case, it's possible to find an open and dense subset when you have this simplicity for every ergodic measure of maximal entropy. And again, the key point is to observe that you are going to stay in this relation. When you perturb the point, the new measures of maximal entropy are going to be, again, homoclinically related to the point. And this, again, was explained for Juan Carlos in the talk last week, okay?
It's CR open, it's not C1 open or anything?
Yes, I always, the problem now, because you need, for the continuity of the holonomies, you need to the C2 norm to be bounded. So it's C1 open among the C2 with bounded norm. So let me state the result for the volume preserving setting. So there are going to be a lot of hypotheses, but let me write it first, and then we can discuss every one of them. The setting is for partial hyperbolic. With two-dimensional center bundle. I'm going to ask for the classical hypothesis of center banded and accessibility. I'm going to ask for the starting map to be symplectic, but I'm going to perturb among volume preserving one. I'm just asking for the first one to be symplectic. It has at least one periodic point. Since I'm the partial hyperbolic setting, I need to ask for this. And I'm going to ask for the differential to be conformal in the stable and unstable bundles. Then F can be CR approximated by open sets with simple Lyapunov spectrum, open set of volume preserving. with simple Lyapunov spectrum. In each one of them. This. I'm going to explain where I'm using this, okay? Okay, so let me make some comments about the hypothesis. First, I don't want to raise, okay. These hypotheses are all C1 open, partially parabolic, not all of them. The one that I'm going to mention, partially parabolic with 2 center dimensions. Center bunching and accessibility are open conditions. Accessibility is open because I'm in 2-dimensional center. This is a result of Avila and Viana. Moreover, for the result of Burns-Wilkinson, every map here is going to be ergodic, and every map near C2 near them is going to be ergodic also because center bunching and accessibility is going to be preserved. So I have remark. And the other observation is that there are several hypotheses here, but this is a non-empty set. It's possible to construct in the torus a skew product that satisfies this condition. So, and we want to give the proof of this result. I want to obtain simplicity in an open and dense set. So I'm going to perturb this to apply and apply the criterion. So the criterion was for non-uniform hyperbolic maps. So I'm going to do 2 perturbations. First one, I'm going to perturb this and approximate it by open sets of non-uniform hyperbolic maps. And then I'm going to use the criterion and perturb again, okay? So the proof has 2 steps. First one is that there exists, let me write like this, F can be CR approximated by open sets of volume preserving with the following characteristic. This open set is going to be, the maps in this open set are going to be non-uniform hyperbolic. So I'm preserving the volume preserving. I'm saying that volume in this subset is going to be hyperbolic. It's ergodic because we already see that. And the center Lyapunov exponent, I have 2 of them. Are simple and continuous. Okay? Again, I'm trying to use the criterion, so I need an open set of non-uniform hyperbolic maps in order to apply the criterion. I have ergodicity, I have the hyperbolicity of the measure, I have that it's volume, so it's going to satisfy my hypothesis. And I'm going to need this, I need the simplicity of the center because I have full simplicity, but I'm going to need the continuity of the center Lyapunov exponent. So I'm perturbing the map in order to get non-uniform hyperbolicity, ergodicity, and these good properties of the Lyapunov exponent. This here is a consequence of a result with Xiaoliang and Yang. And this is the first perturbation, okay? I have a sequence, and I have both of them being continuous. I'm in the ergodic setting, so the Lyapunov exponent is not going to depend on the point, and the measure is the same because its volume is fixed. I'm saying this for the two center Lyapunov exponent. Okay? And now I want to apply the criterion to this open set. And as I already mentioned to you, how much time do I have? 9. And I already mentioned to you the pinching and the twisting are okay to find. So this is a non-uniform hyperbolic setting. I'm going to have periodic point. I'm going to have homoclinic points. I can perturb to get the pinching and the twisting condition. But there was this condition about the point being homoclinically related to the measure that I need, okay? So in order to apply the criterion, I need this proposition. If the point is homoclinically related to the measure, and the measure now is volume, then there exists an open set such that for every point here, the continuation of the periodic point is also going to be homoclinically related to the measure, okay? And if you recall the definition of homoclinical related was about transverse intersection of stable and stable manifolds, right? So this is a hyperbolic periodic point. So when I perturb my dynamic, this point is going to have a continuation, and its stable and stable manifolds are going to behave well. The problem is that I need this condition almost every point, and this are Pessin manifolds. So what I need is a good behavior about the Pessin manifolds when I perturb my diffie, okay? And this is achieved by the following result. So before let me erase here. There exists an open set. Yes, this was not really good writing, right? This open set. Oh, original one is here, of course. It was okay. There exists a neighborhood of F. Such that for every map here, we have a Pessin block with at least this measure, okay? So what I'm saying here is that in some sense, we can get Pessin blocks. I'm not being very precise about the quantifiers, but I can do it if you want. But there is a neighborhood of the original map when I know that there are Pessin blocks that has at least this measure. Okay, so this is going to allow me to consider, at least in a positive set measure, a well-behaved stable and stable manifold when I'm perturbing the map. And since in the ergodic setting, this is going to give me the condition that I want, okay? And so the proof of this lemma is a consequence of results that were established by Busi-Krovisier-Sarik in the studying of the SPR property. They have some relation about the stability of the Pessin blocks, and their results allow to prove this lemma, okay? And the key point there is the continuity of the center Lyapunov exponent. You can think that you are in the partial hyperbolic setting, so the stable and stable splitting are going to behave well, and in the center, the continuity of the Lyapunov exponent is going to give you a well behavior of the oscillated splitting in the center. And this is going to allow you to get the information about the Pessin blocks, okay? And so the theorem has all these hypotheses, but that was because in this setting, we are able to get an open set when we have these good properties that we need, okay? What we need actually is non-uniform hyperbolicity, ergodicity, and a good behavior of the center Lyapunov exponent, okay? Okay, so I'm going to finish here. Thank you.
Questions?
Where you can go out from the symplectic setting. So this is the conclusion is beyond the symplectic setting, right?
Yes, it's for the volume.
So
setting.
that's part that you want to get continuity and
I
this
want, yes, I
intersection.
want simplicity and continuity of the central Lyapunov exponent. If I start with the symplectic and I prove the simplicity is going to give me non-zero for both. If I start with the volume preserving, no. So I only know how to get non-uniform hyperbolic when I start with the symplectic one. But then the perturbation is volume preserving.
Eji?
Can you explain a little bit about this remark about you cannot apply this codification when you try to perturbate the map?
No, I was saying that the coding is going to depend on the map.
Yes, yes.
Yes? So if there is no way to state the criteria, you can do that. You can do that. That is what they did in the paper that I mentioned. You code first, and then you check that your map in the coding satisfies some condition. But the problem is when you want to prove that, you perturb, and you need information about which is the coding, how the coding is behaving when you change the map in order to test that it verifies what you need.
So there is no continuity in the coding. There is no possible, I think. No. If you perturb your map, you perturb your coding.
Yes, and you do not have information how the coding is changing.
You don't have any hypothesis to guarantee the
No.
continuity of the coding. Okay. Thank you.
Karina, where did you use the conformability?
Yes, I realized that I didn't say anything about that because I was erasing. I'm going to perturb there. I'm going to get these subsets. I'm going to have the stability of the monoclinic relation. I'm going to apply the criterion. The criterion was asking for the linear cocycle to be fiber bunched. So I'm going to apply the criterion to the derivative restricted to EU and the derivative restricted to ES. I need for these cocycles to be fiber bunched. I could write that, but I can say conformally, and since the perturbation is near conformally, I'm going to have what I need.
And second, this result in the lemma is a quite general, on the very general hypothesis, but perhaps it is a question for... No, the lemma that you, about the Pessin blocks.
The lemma is about, what I need is hyperbolicity, ergodicity, and continuity of the center Lyapunov exponent.
Thank you.
Any other question? I actually have a question. Can you do this for endomorphisms?
I don't know. I think that the criterion, I don't know.
Okay. And the other question is that chi over 2 is important or in the criterion?
Yes, because if you recall, I was saying, I have that, the measure was chi hyperbolic, right? But I was asking chi over 2 fiber bunches for the linear cocycle. This is because when I'm going to leave the linear cocycle, the regularity of the linear cocycle is going to depend on the regularity of the coding. So that's the difference, okay?
But could it be anything smaller or?
Could be anything smaller.
Okay. Okay, so let's thank Karina again.